So part 2, number 1. Water tank has a shape of an inverted circular cone with a base of 20 meters and a height of 40 meters. It's being filled with water. At any given moment, the water inside the tank also forms a cone with changing radii r and height water level h. So r is the radius of the cone of water and h is the height of the cone of water, which of course is different from the radius of the cone like container and the height of the cone container. At the moment when the water level is 6 meters high, the water level is rising at 1/2 meters per minute. Suppose you wanted to find the rate at which the volume of the water in the tank is growing. So first of all, they want us to find the derivative of the volume function. You have to use the product rule because r is a function, h is a function. So I think we get 2/3 pi r times dr dt times h left alone plus 1/3 pi r squared dh dt. So that's our derivative formula. We are being asked to find the rate at which the volume of water is changing. So we want dv dt. What do we know? Well, let's see. Not very much. Be careful because like this 20 that they're giving you is not the current value of r, and this 40 they're giving you is not the current value of h, because r and h refer to the dimensions like the size of the water, not you know what I mean? In 20 and 40, that's not the dimensions of the water. That's the dimensions of the cone container. We do know that at this current moment, the water level is 6 meters. So I think right now h is 6, and the water level is rising at 1/2 minutes or meters per minute. So I think that's saying that dh dt is 0.5, but that's all that we know. And if we look at this equation, this is what we want, but we do not know r and we do not know dr dt. So there's quite a lot that we don't know in this equation. And this problem is pretty tricky because to find those things, you actually have to use a totally different equation, and we guide you through it. Basically, what you should notice is that if you focus on this little slice here, that's like a two-dimensional slice of the 3D picture, you have similar triangles, which means we can say, for example, this side compared with this side should be equal to this side compared with that side. So therefore, r over 20 should be equal to h over 40, which means, you know, if we like multiply both sides by 40, then I think we get 2r is equal to h. So that's a relationship between r and h, and that's the equation you need to use. Right away, since h is equal to 6, you can use this equation to find r. So 2r is equal to 6, which means that r is equal to 3. So that's cool. So now we know what r is, but what about dr dt? We also, you know, dr dt appears in this equation and we don't know what that is. Well, you can find it by taking the derivative of both sides of this equation. If you take the derivative of both sides of this equation, then you get 2 dr dt equals dh dt, and we know what dh dt is. That's 0.5. So if I replace, then I find 2 dr dt is equal to 0.5, which means that dr dt is equal to 0.5 over 2. So dr dt is 0.25. Okay, so cool. I think with that, we know everything else, right? So we want dv dt. That's 2/3 pi r. Do we know what r is? Yep, it's 3. Do we know what dr dt is? Yep, it's 0.25. Do we know what h is? Yeah, it's 6. R we know, and dh dt we know is 0.5. So yeah, now it's just a matter of plugging all those things in. So that's number 1. I'll let you do the rest. Number 2, as a spherical snowball melts, its surface area decreases by 1 square centimeter per minute. At what rate is its volume decreasing when the radius is 4 centimeters? And then if you notice, there's a hint here. It's very small on my screen, but it says the surface area of a sphere is given by a equals 4 pi r squared, and its volume is given by v is equal to 4/3 pi r cubed. Remember, we'll always give you those kinds of formulas. 3D formulas we'll always give to you, so you don't need to know those. So they give me these two formulas. The surface area is 4 pi r squared, and the volume of the sphere is 4/3 pi r cubed. Apparently we need both of those. So what do we know here? We know that the surface area is decreasing by 1 square centimeter per minute. I think that means dA dt, the rate of change of the surface area, is -1 because it's decreasing. And I think we also know that at this moment in time, the radius is 4. So I also know that r is 4, and like that's it. And I want to know at what rate is the volume decreasing, so I want dv dt. So like I can, take the derivative of both sides of this equation, but I have a feeling I'm going to have to use that equation, right? So like if I take the derivative of both sides of the volume equation, I get dv dt, which is what I'm trying to find, equals, I think, just 4 pi r squared dr dt, because the 3 cancels with the 3 in the denominator there. So this is what I want, and I know what r is at this moment, but I don't know what dr dt is. So I think I have to use the other equation to figure that out. Like dr dt does not appear in this equation, so I think to get an equation involving dr dt, I have to take the derivative of this guy. So let's take the derivative of the surface area equation. What would that give me? That would give me dA dt is equal to 8 pi r dr dt. Okay, and let's see. I know that dA dt is -1, so that means -1 is equal to 8 pi times r, which is 4, dr dt, which means that dr dt is -1 over 32 pi. So, whatever number that is. If I then return to this equation here, dv dt is what I'm looking for. Let's see, that's 4 times pi times r squared. Do I know what r is? Yeah, it's 4. And do I know what dr dt is? Yeah, I just figured out that it's this number here. So if you plug all that stuff in, then you should get the answer, no problem. Number 3, Billy's father. Billy, I love this joke because you're finally introduced to someone else in the Billy extended universe, but that person's name is also just Billy. It's a great joke. As he fights a fire, the ladder both extends, so the ladder's like getting longer, but like also it's kind of rotating, like it's going up, so ladder's getting longer this way, but also this angle is increasing, so it's sort of extending, but also getting more vertical at the same time. So the ladder extends at a constant 4 feet per minute. Looks like they've given us some variable names already, so we should use those. So the ladder is extending to constant 4 feet per minute. I think that means that dz dt is 4. At the moment, be careful with this language here. You might see the word constant and be like, oh, that means dz dt is 0. No, it's not saying z is constant. It's saying the rate of change is constantly 4. If z were constantly 4, then yeah, the derivative would be 0. But it's not that z is constantly 4. It's that the derivative, the rate of change, is always the same. Anyway, at some moment, the angle is 1.2 radians, so theta is 1.2. by the way, like when they say theta is 1.2, they mean 1.2. It doesn't mean 1.2 pi. Like don't insert a pi or something there. Okay, Billy's dad is 6 feet above the truck. So I think that means that at this moment h is 6. And he's rising by 10 feet per minute. So I think that means dh dt is 10. Okay. Let's determine at what rate the ladder is rotating. So it sounds to me like we want d theta dt. So, you know, if we look at the quantities involved, we've got like h, we've got z, and we've got theta. We need a trig equation which relates those three things, right? So like you might think, oh, maybe it's the Pythagorean theorem, but no, because like that wouldn't involve theta, right? Like your equation needs to involve theta. So it's got to be some kind of a trig function. Notice that compared to theta, this side h is the opposite side, and this side here, z, that's the hypotenuse. So which trig function involves opposite and hypotenuse? That would be sine. So you want to say sine of theta is equal to the opposite side, which is h, divided by the hypotenuse, which is z. So that's the function that we're looking for. That's the answer to part A. Like they just want you to write down the appropriate equation. They say in part B that you should rewrite this expression as a product instead of a quotient to make it easier to take the derivative. You don't have to do that. Like you could take the derivative of both sides of this equation as it is, but you would wind up having to use the quotient rule, which is like okay. You'd get cosine theta times d theta dt. I'll just show you, what it looks like just in case you want to do it that way. Equals, it would be dh dt times z left alone minus h left alone times dz dt all over z squared. That equation will work, but it's actually a little easier if you multiply both sides by z first and then use the product rule. And if you take the derivative that way, then you find dz dt times sine theta left alone plus z times cosine theta d theta dt. Damn it. D theta dt equals dh dt. So you can use like either one of these equations. You don't need both. Like, the only thing we're saying about multiplying both sides by z is I think for most people like this derivative would be easier, although like I don't know, maybe not. Whatever, you can use either one of those equations. I'll go with this one since you're probably using this one. Okay, now find d theta dt. Well, d theta dt is right here. Right? There it is. Do we know everything else in this equation? Well, dz dt, yeah, we know what that is. That's 4. Sine theta, well, I actually know what theta is. So, like, I can just plug in 1.2 for that, so no problem. Plus z, do I know what z is? Oh, I actually don't. I don't know what z is at this moment. So I think I'm going to have to find that by returning to the original equation, this guy right here, right? Or this one, or whatever, it doesn't matter. So if you if you return to this equation or this equation and you plug in what we know, then you can find z. Like if I use this one here, then I'll find z sine of 1.2 is equal to h, which is 6. So therefore, like, z will be 6 over sine of 1.2, whatever number that is, I don't know. At any rate, that gives you z cosine theta. Yeah, we know what that is. We know what cosine theta is. And d theta dt, that's the thing we're trying to find, so that should be unknown. And dh dt, do we know what that is? Yeah, that's 10. So you know everything in this equation, so now it's just a matter of plugging in and solving. You guys can do that on your own. Okay, number 4. This is just like a regular implicit differentiation problem. So pretty much if you see x's and y's, Like, can we say find dy dx? It's a, it's an implicit differentiation problem. So, okay, so 1/2 y squared plus 8 equals xy, and we're going to find dy dx. So we're just finding the general derivative, not the derivative at any particular point. So I take the derivative of both sides, being careful to remember that, as this notation indicates, y is a function, and x is a variable. So the derivative of the first term is not just y, but y prime, right? Because of the chain rule. Derivative of 8 is 0. The derivative of the right-hand side, you have to use the product rule. Watch out for this. This is the thing you're going to mess up on the test, or that you're most likely to mess up on the test. Product rule says, okay, derivative of x is 1, because it's a variable. It's not x prime or something. Derivative of x is 1 times y left alone, plus x left alone times the derivative of y, which is y prime. Then we put all the stuff involving y prime on one side of the equation, equals y, factor out the y prime, then we divide, and we get this guy right here. So that's the formula. That's the general formula for dy dx, or y prime, same thing. Why does it skip to number 8? I don't know. Because I deleted questions and didn't feel like renumbering, I guess. Number 8, Anneliese is looking for her cousins Hansel and Gretel. The gingerbread house is at 0. So I guess we're supposed to imagine this is like a number line. Units are in miles and hours. Anneliese's position is given by this function right here. A, discuss her position, velocity, and acceleration at t equals 2. Reading ahead, like, I guess to do that, it's interesting. They're just asking about what's going on at one specific time. So, like, for this part of the problem, I actually don't need any number lines. Like, I just need to plug 2 into the position function and the velocity function and the acceleration function. So like x of t is t cubed minus 9t squared. So therefore x of 2 is just 8 minus 9 times 4, which is 8 minus 36, which is negative 32, which means, like, I guess in the context of the problem, Anneliese is located 32 miles west of the gingerbread house. The velocity function is going to be given by x prime, which is 3t squared minus 18t, and x prime of 2 would therefore be 3 times 4 minus 18 times 2, which would be 12 minus 36, which is negative 24. So I guess that means that she's moving 24 miles per hour in the western direction because the velocity is negative, so she's like moving to the left. And then x double prime of t is 6t minus 18, and x double prime of t, or of 2, excuse me, is 6 times 2 minus 18, so that's 12 minus 18, which is negative 6. So her acceleration is negative 6. The units for acceleration here would be miles per hours squared. It's like miles per hour. It's like how much velocity you're picking up each hour. Yeah, so there they are. Like, we don't need a number line for this part, but we are going to need one for the next parts. So next part, find all the intervals when she's moving away. What time intervals is she slowing down? Blah blah blah. Like, let's just do number lines, like a sign analysis for each of these 3 functions. So for x of t, if I set it equal to 0, I have t cubed minus 9t squared is equal to 0. So therefore, I can plot a common factor of t squared. I get 2 solutions. One is 0, and the other one is 9. The number line, I think I'm going to write the number lines like here or something. So x of t, the number line looks like this. 0, and then maybe out here is 9. Okay, let's do a test point. I like 1. I can't do 0 because 0 is like a boundary point, but I can do 1. If I plug in 1, I get 1 cubed minus 9 times 1. That's going to be a negative number, which means that the position is negative in this region. You could do test points for the other regions, but I'm going to use multiplicity. 0 comes from the t squared. Because that is being raised to an even exponent, I know that the sign will not change at 0. So like I know it's going to be minus in this region as well. And then 9 comes from this factor, which has like a 1 for an exponent. That's odd, so it is going to change there. So that's the sign analysis for the position function, and I'll kind of leave that there. Okay, for the velocity function, I need to set 3t squared minus 18t equal to 0. Pull out the common, well, it's a common factor of t, or you could also say 3t, whatever, t minus 6 equals 0. So I get two solutions, 0 and 6. And I'm going to put my number lines close to each other. Like I like to be able to see them all at once. So here's my sign analysis for velocity. We've got 0 and we've got 6. Okay, so test points, I don't know, let me do 1 maybe. If I plug 1 into this guy, then I get a negative number. So the velocity is negative on this region. 0 comes from this factor, which has an odd multiplicity, so the sign changes there, so it has to be a plus, and it also changes at the 6, so it's got to be a plus here. Finally, x double prime, which is 6t minus 18. So sign analysis for x double prime, 6t minus 18, right? Yeah, equals 0, so that gives me, I mean, you can solve this in lots of different ways, but, you know, you could just add 18 and divide by 6 if you wanted, that'd be fine. At any rate, you get t is equal to 3. So our sign analysis, our number line for x double prime, the acceleration, has just one value at 3. And if I pick a test point, like say 1 or something, then I plug it into the acceleration function, I get a negative number. So therefore it's negative on this region. Nope, that's not what I wanted, Microsoft Word. Why are you doing that? You don't need to do that. Oh, let me help you. Let me help you. It's, yeah, stop it. Stop that. Stupid. Okay, and then after 3, I think it changes to positive. So, okay, so I've got the sign analyses for all 3 functions, and I've got them stacked and aligned on top of each other, which, like, you're really going to want for the problems that involve, like, more than one number line. Okay, so when is she moving away from the gingerbread house? Moving away from the, I mean, the gingerbread house is located at the origin, so that's just asking when is she moving away from the origin. That occurs when position and velocity have the same sign. So, yeah, so like when does that happen? So I'm just focusing on these two number lines here. When do these guys have the same sign? Not to the left of 0, but between 0 and 6, they're both negative. So between 0 and 6, definitely. Not between 6 and 9, because this guy's positive, but this guy's negative. But then after 9, they're both positive. So those are the two intervals on which she's moving away. Okay, and what time intervals is she slowing down? Okay, well, slowing down means velocity and acceleration have opposite signs. So I'm going to focus on these two number lines for this question. So when do they have opposite signs? To the left of 0, but I don't know if that's a valid time interval. Like, I don't know if time begins at 0. It doesn't say anything. So, whatever. Yeah, like, I don't know if negative time values are legit in this problem, but, like, if they are, then during those time intervals, like before 0, the velocity and acceleration have opposite signs, so they'd be slowing down. Okay, and then when else? Well, not between 0 and 3, because these two guys have the same sign during that time. But then between 3 and 6, this guy's negative and this guy's positive, so she's slowing down during this time interval. But then after 6, they're both positive, so not during then. So that's when she's slowing down. Finally, find her distance traveled and displacement from noon to 10. I have got to say, I kind of feel like there's a little bit of missing information here. Maybe you didn't notice this, but like, whenever we give you a word problem like this, we kind of have to tell you what time means. Like, we tell you that time is measured in hours, but like, time has to be, it can't just mean hours. It has to be hours past some fixed moment. So like, does this position function, does let me put it this way, does time represent number of hours past noon? Does t represent number of hours past midnight? It doesn't say, and it really should, because when it comes time to like, oh, find our distance traveled and displacement from noon to 10 p.m. Okay, but like, how do we represent 10 p.m., right? Like, does that correspond to t equals 10 because it's 10 hours past noon? Or does that correspond to t equals 22 because that's 22 hours past midnight? Do you see what I'm saying? So I don't really know. I assume they probably intend for t to represent hours past noon in this problem, is what I'm guessing, which means that noon corresponds to t equals 0 and 10 p.m. corresponds to t equals 10. But they really should tell you that. So whatever. Yeah, so part D. Okay, so displacement over from noon to 10, so we're saying that's from 0 to 10. That's easy. That's just x of 10 minus x of 0. So x is this function right here. Plug in 10, plug in 0, subtract. I don't know. Like, whatever. You can do the arithmetic on your own. Distance traveled is trickier because we have to think about when is she moving left and when is she moving right. And then we have to compute the displacements over each of those time intervals, like how far did she go left, how far did she go right. And to figure out the time intervals of one directional motion, we have to look at the number line for the velocity function, this guy right here. So we can see that, I mean, before 0 is not really under consideration here because we're computing distance traveled from time 0 to time 10. But yeah, initially she's moving to the left, but then at 6 she turns around and she's moving to the right. Okay, so we have two intervals of time that we have to consider, 0 to 6 and then 6 to 10. And we've got to compute the displacement over each of those separately. So displacement over 0 to 6, that would of course be x of 6 minus x of 0. And remember, you're plugging 6 and 0 not into the velocity function, right? You are like x of 6 and x of 0. You're plugging those numbers into the position function, okay? Like maybe you used the velocity number line to find the interval 0 to 6, but you're using the position function to compute the displacement. So what number does this give you? I don't know. I don't really care. Like, you can do it yourself. It's going to be negative because she's traveling to the left during this time, which means that the displacement is going to be negative. So it's going to be some negative number. And for the purposes of distance traveled, you want to take the absolute value of that. You want to make it positive. Then we do the displacement over the other interval from 6 to 10, which would be x of 10 minus x of 6. And you just take these two numbers, make sure they're both positive, add them together. That's the distance traveled. Okay, 9. Each graph below shows position function for a baby dinosaur. For each circle, the answers. Okay, so x3. X of 3. I mean, this is a graph of x, right? This is a graph of the position function. So this is a graph of x. So is x itself positive or negative at 3? Positive, like it's a graph of x, and the value of this function, like the y coordinate, is positive, so definitely positive. X prime, well, that's the derivative of the function whose graph we're looking at, so that's the slope. And the slope looks negative. X double prime, that's the acceleration. You can say to yourself, a second derivative is positive just means the graph is happy, and second derivative is negative just means the graph is like a frowny face. Is this like a smiley face or a frowny face? It's like a frown. Okay, do you see how it's curving down like that? So that's like a frown. I mean, it's not a whole frown, right? Like this would be a whole frown, but it's half a frown. So x double prime is negative. Or you can say to yourself, like, x double prime negative means that x single prime is decreasing. And you can see that the slope is indeed decreasing because, like, at first the slope is a small negative number, but then later on it's a larger negative number, so that's a decrease. Speeding up and slowing down, I mean, like, I think you can kind of look at the graph and, like, intuit that it's speeding up. Because, like, at first the position isn't changing very much, but then, like, you can see that the position is kind of changing rapidly. You know what I mean? Like, in this region. But, you know, if you want, you can say, oh, speeding up, slowing down, that depends upon whether um, whether the velocity and acceleration have the same sign or opposite sign. You know, well, velocity is negative and acceleration is also negative, so she's speeding up. You know what I mean? So she's speeding up. Okay. Moving toward or away from the origin. Like, look, this is a graph of the position function. Like, it's a graph of the x coordinate of the baby dinosaur. So, like, the baby dinosaur is at the origin at this moment right here. Okay, is the baby dinosaur getting closer to the origin, you know, or further away? Well, certainly closer. You know what I mean? Like, it's obviously getting closer to this horizontal line here. But you can also say, oh, well, toward away from the origin, that means whether the position and velocity function have the same sign or opposite signs. And you've already done the necessary analysis here. Like, the position is positive, but the velocity is negative. They have opposite signs. So therefore, towards the origin. Okay. Um, okay, B. I mean, this is pretty much the same kind of problem. Okay, is the position positive or negative? It's negative. This is a graph of position, so it's talking about the y-coordinate. X prime, that's talking about the derivative, so the slope. The slope is definitely positive. Second derivative, well, the graph is happy, right? So second derivative is positive. Alternatively, you can say to yourself, hey, like the slope here is like only a little bit positive, but then here I think it's a bit more positive, so that's an increase. So x prime is increasing, which means its derivative, x double prime, must be positive. Is it speeding up or slowing down? To me, intuitively, it's clear that it's speeding up. Like it just like I just look at the graph and I'm like, yeah, it's sort of moving faster here than it was over here. Like here, it's not moving very quickly, and then here is it. But you can also be like, oh well, you know, the acceleration is positive and the velocity is also positive. Since those two things have the same sign, that means it's speeding up. You know, towards or away, again, like, look, being at the origin just means like the dinosaur is at the origin at this moment right here. Like it's a graph of the x coordinate. Being at the origin means you're like at this axis here, and the object is obviously getting closer to the axis right at this time. Or you can say like, oh, the position is negative, but the velocity is positive. So position and velocity have opposite signs, so therefore it's moving towards the origin. Oh my god. All right. The radius r of a sphere is increasing at the uniform rate of blah blah blah. At the instant when the surface area S becomes 100 pi square inches, what is the rate of increase in cubic inches per second in the volume V? Okay, so this is AP 26. Yeah, so we got these two formulas. I guess we're going to need both of them. So what do we know? We know that the radius is increasing by 0.3 inches per second. So I think drdt is 0.3. Also, at this moment, the surface area, which they're calling S, is 100 pi. That's all we know. And what we want is the rate of increase in the volume. So we want dv dt. Well, you know, I'm going to need... So if I take the derivative of this equation, I'll get a formula for dv dt. So I'll get dv dt equals, I think, 4 pi r squared dr dt. So this is what I want, but I think I don't know what R is, right? I don't know what R is, and I need to find it. So I can find it by going to this equation. Interestingly, I actually don't think you need the derivative of this equation for this problem. Like, I don't even think that you need the derivative of this guy, because all I'm missing is R, and I can find R from just the original equation, because I know that S is 100 pi equals 4 pi R squared, so divide both sides by 4 pi. I think I get 25 is equal to R squared, so R is equal to, well, plus or minus 5, but context, obviously R is a positive number. So R is 5. Okay, so now you know everything you need to know in this equation to find dv dt, so you just plug in. Yeah, so you don't even need the derivative of this guy. So that's, I'll let you finish it up. AP 21. Functions w, x, and y are differentiable with respect to time and are related by the equation w equals x squared y. Okay. If x is decreasing... Okay, this is a related rates problem, except with no physical context whatsoever. It's a related rates problem, but like without any associated word problem, essentially. It's a related rates problem that's been stripped down because they just tell you that w, x, and y are all differentiable with respect to time. So they're telling you they are functions of time. And these three functions are related by this equation here. Careful, like x is not the variable here. X is a function of time like w and y are. And it tells you that x is decreasing at a constant rate of 1 unit per minute. So dx dt is -1 because it's decreasing. And y is increasing at a constant rate, so dy dt is 4. At what rate is w changing with respect to time when x is 6 and y is 20? So yeah, so I know these two things here, and I also know that x is 6 and I know that y is 20. Okay, so I want the rate at which w is changing. That's dw dt. I can take the derivative of both sides of this equation. Be careful, you got to use the product rule here. So I think we get dw dt equals 2x dx dt y plus x squared dy dt. So let's see. This is the thing that I want. Do I know everybody else? Do I know what x is? Yeah. Do I know what dx dt is? Yeah. Do I know what y is? Yeah. Do I know what x is? Yeah. Do I know what dy dt is? Yeah. So at this point, you just plug in. Okay, so that's it. You can do that on your own. AP 34. The top of a 25-foot ladder is sliding down a vertical wall at a constant rate. We did a problem like this. You should go back and look at it. Like, if you want some guidance, it was on the first day of related rates. But basically, you know, the picture that you should have is like, you know, so here's the floor, here's the wall, and then like here's the ladder. So the ladder is 25 feet long. So this side of the right triangle is 25. I'm drawing with my trackpad on my laptop, so excuse the crappy drawings. And that's constantly 25. Like, that's not changing. So I'm not going to give this side of the triangle a variable name because it's not actually a variable. You know, like that's just not changing at all. I'm not going to call it H or anything like that. Okay, but these two sides of the, you know, this is a right triangle, right? These two sides of the right triangle, maybe I'll call them x and y, those guys are changing. So, yeah, so like it's sliding down the wall, so like this point right here is kind of going down, which means that this side of the triangle is decreasing in size, and like meanwhile, this side of the ladder is going to be sliding this way. So like I think this side of the triangle is increasing. So anyway, why is it moving? What? Okay. What? Why does it regard that little piece as somehow like separate from the rest of it? Can I group these? So strange. Okay. Oh God. God help us all. I know I shouldn't have drawn anything. That was a mistake. Oh, I can't even... Okay, whatever, fine. This image is just going to move as I type. Yeah, so I think you want to just do Pythagorean theorem. And, yeah, oh, like, what do we know? We know that at this moment, y is 7. And what we want is how fast is the bottom... What is the rate of change of the distance between the bottom of the ladder and the wall? So that's dx dt. So here's my equation. If I take the derivative of both sides, I get 2x dx dt plus 2y dy dt equals 0, because that's a constant. I want dx dt. That's right there. Am I missing something? I think I'm missing something, right? I didn't... Yeah. The ladder is sliding down the vertical wall at a constant rate of 3 feet per second. So that means that dy dt is -3. Negative because this side of the triangle is decreasing by 3 feet per second. So, so dx dt is what I want. Do I know everything else? No. I don't know what x is. I need to figure out what x is. But I can do that by going back to this equation, right? So I can say x squared plus y squared, which is 7, is equal to 25 squared. I don't know what that's going to give me. X squared is equal to 25. Oh, this is a non-calculator problem in the AP. That's rather rude of them. You're supposed to do 25 squared. I don't feel like doing that, okay? Sorry, guys. So that's evidently 576, and the square root of 500... Like, that seems like a bit much. You know what I mean? Like, why would you... So it's 24, but like, how would you... I mean, you could do it, but my God. Whatever. Anyway, so x is 24. So now you know everything you need to know in this equation to find dx dt. So you're all set. 88. This is a problem that everybody always gets stuck on. Okay, I'm just going to delete you. Oh, you don't want to be deleted. What in God's name? So strange. Anyway, okay, so 88, this is a hard problem. You got to use similar triangles. All right, let me just do a little drawing here. Wow. Okay, there we go. All right, this is a right triangle, and this is also a right triangle. And do you see the big triangle here? And then the smaller triangle here? These are similar triangles. So, oh, I drew this kind of badly, because the shadow is actually drawn in the diagram. So the light beam goes, crap, the light beam goes like this. Yeah. All right. Yeah, so there's a right triangle, there's a right triangle. All right. So the person's height is 6. So that guy is just constantly 6. That's not changing. The height of the streetlight is 15. So this is just constantly 15. Cool. And then it says, what is the rate? The person's walking away from the base of the streetlight at 4 feet per second, and they want to know the rate of change of the shadow. So, let me call the shadow, the length of the shadow, which is this thing right here. Let me call that S for shadow. And I think like this side is also changing, like this guy right here, which is the distance between the street light and the person. I'll call that, I don't know, X maybe. And so here's what I know. I mean, beyond the fact that this is 15 and this is 6, the person's walking 6 feet per second away from the lamp, which means that X is getting bigger. by 4 feet per second. So dx dt is 4. And what I want is the rate of change of the shadow, so ds dt. Now, what's the relationship between x and s? It's like not obvious, but it's similar triangles. So you can be like, this side here compared with, or you can be like, this little side right here compared with this side should be the same as this big side here compared with this big side here. You can do stuff like that. Or you could say 6 compared with 15 is the same as this side compared with this side. I feel like that's kind of more natural. Let's do that. So 6 compared with 15 should be the same as this little piece right here, which is s, compared with this whole piece here, which is x plus s. All right, and that's the equation. I would clear denominators. So like 6 times x plus s is equal to 15s. That's like cross multiplying. So 6x plus 6s is equal to 15s. And then if you subtract 6s from both sides, you get 6x is equal to 9s. And that's the equation that we want. Now, if you take the derivative of both sides, you find 6 dx dt is equal to 9 ds dt. We know that dx dt is 4, and ds dt is what we want. So after that, you can just plug in. Okay, 18, last problem, finally. F of x is sine of x over 2. This is, or no, it's not. Then there exists a number c in the interval blah, blah, blah that satisfies the conclusion of the mean value theorem. Which of the following could be c? So, of course, the mean value theorem says, look at the average rate of change of this function over this interval. Whatever that number is, there's going to be a moment c at which the derivative matches that number. So let's compute the average rate of change over the interval from pi over 2 to 3 pi over 2. That's going to be f of 3 pi over 2 minus f of pi over 2 over 3 pi over 2 minus pi over 2. Which is, so in the denominator, 3 pi over 2 minus pi over 2 is 2 pi over 2, which is just pi. In the denominator, f of 3 pi over 2, that would be sine of 3 pi over 4 minus f of pi over 2, that would be sine of pi over 4. So that would be sine 3 pi over 4. Oh, sine of 3 pi over 4 is root 2 over 2, and sine of pi over 4 is also root 2 over 2. So this numerator is 0, which means the whole thing's 0. So the average rate of change is 0. So we are looking, so the mean value theorem says there exists a c such that like f prime of c will be 0, right? So what's the c value? Well, to find out, we just take the derivative and set it equal to 0 and solve. So the derivative, notice this function is a composition, so you have to do the chain rule. So the derivative is cosine of x over 2 times 1/2. It's like a, because this is like sine of 1/2 x. So set this guy equal to 0, not that it really matters actually. We get cosine of x over 2 is equal to 0. You might wonder like, oh, how do I solve this trig equation? I wouldn't worry about solving the trig equation per se. Like you could, this is saying that x over 2 is an angle whose cosine is 0. So x over 2 could be like pi over 2, for example. Or you could just like see which of these values satisfies the equation. Like you could just look at them and see which one works. But like formally, the way to solve an equation like this is to say, okay, this equation says x over 2 is an angle whose cosine is 0. So that means x over 2 must be like, well, when is cosine 0? Well, pi over 2, or alternatively, x is equal to 3 pi over 2. And if I solve those equations, I get x equals pi or x is equal to, or sorry, x over 2 is pi over 2, or x over 2 is equal to 3 pi over 2. So I get x is equal to pi, or x is equal to 3 pi, but like that number is not inside this interval, so like that's not the one that the mean value theorem is talking about, so it's this guy, so it's pi. Okay, all right, that is it, guys.